in this example number 5, you're going to understand and learn how to use the energy equation and Bernoulli. Actually, we're going to put all the other other two conservation theories together. For this particular problem, we are going to consider the following case. You're going to consider there is a flow coming here. There's an airflow coming in this direction, and there's an airflow coming out of this direction. Um, and what we are really trying to do is we are trying to find how much is this force F. This is the goal. This is what we want to find. And we will consider gravity. So gravity is acting on the system. Um, and what is known in the problem? We know V1. So this is V1. This is V2. The area is delta S2. This area is delta S1. The pressure acting in the opening here is P1. Pressure acting here is P2 in this opening. And what is known in the problem, V1 is known, your pressure 1 is known, height H is known, and you know your delta S1, you know your delta S2. I'm sorry, 1 and 2, okay? So these are known values, so you know everything. We can assumption that density is constant. We can assume that Q is equal to 0, no heat transfer. Okay. No viscosity. At the walls, so no shear. The other thing we can also assume in the problem is that it's a frictional flow, it's incompressible flow, and these consequences allow me that my energy equation becomes my Bernoulli equation. Okay. Now, if any of these were not true, then I have to use the energy equation. That's the most general form of the equation. So in this case, since these conditions are true, and we can assume that I'm moving along the fluid line as well, then I can assume that I can just use the Bernoulli equation for this. Okay, and there's one more thing here, that this is steady state. It's a steady flow. Okay, so this is also an assumption that we will make. So when I start this problem, so let's change colors. What I'm really looking for, we want to find your F. This is the main goal. However, to find your F, we need to know all these quantities. What I do not know? Well, I do not know V2, so I need to find the velocity here. I do not know P2. I know P1. I do not know P2. If I knew everything, then I can find this, right? So what do we know that we can use to find this? Well, I got this. I have the velocity. I have the area. I have the density. The density is the same. So I could use conservation of mass. Okay. And then to use P2, I could use Bernoulli equation to use P2. The Bernoulli equation will let me find the pressure that I'm looking for. And then this, how do I find this one? This one will be using the conservation of momentum. So the big question is, which equation do I use first? What do I use second, right? So first of all, your momentum equation, okay, so let's see, understand this. Your momentum equation, to do your conservation of momentum, you need pressure, you need velocity, to find your force. Okay, and then Bernoulli equation, well, actually, this uses, just put general, uses all these quantities, right? And also uses unit vector, uses your delta S. The Bernoulli equation uses P, uses V, and uses your Z location, right? This is your height, um, H. And then your mass, conservation of mass, uses your velocity, uses density. This also uses density and uses delta S. So if you look at the problem, right, here to use the momentum, I need to have all these quantities. Bernoulli, I need to have all these quantities. So let's see what I have and what I don't have. In the problem, I have, we just found here, I need to find V2. So I do not have V2. This is not known. I do not know what my P2 is. I do not know. So if I knew all my velocities, I can find this, right? So this cannot be a first option because I do not know neither V, neither I know P. I could go to the Bernoulli equation, right? So in other words, to find F, I need to have at least all my P, P1, P2, and I need to have V1 and V2. But these two are not known. Okay? Now, if I go to the Bernoulli equation, I can say, hey, wait, I do not know to find, let's say I want to find P2 using Bernoulli equation. Um, but I need to know P1, I need to know V1 and V2, but I do not know V2. Okay. Now in this equation, I can say, hey, I can't find V2 because I have V1. This is basically what it depends on. And so I have all these quantities, right? So I have all these, I can find then V2. So the process that we're going to go through is we find the mass first, find your V2, come up here, find your pressure, and then come back up here and finish up with the momentum. That's the order in which we will do the problem. So let's go and start. Then the first task we're going to do is we're going to use the conservation of mass. And the conservation of mass in the most general form says this is a derivative of rho respect to time over volume plus the enclosed area dot ns is equal to 0. Okay, this is equal to 0 because it's steady. Remember, the flow is steady and your rho is also constant because the rho is not changing. And then this particular the enclosed area, the pressure, sorry, this is density. This is density. Density times velocity, dot product velocity and unit vector over the enclosed area is nothing else than the summation of I equal to 1. In this case, how many openings I have? I have 1 and 2. So I will put here 2. There will be rho I times Vi dot Ni delta SI. Okay, so in our particular problem, let's go ahead and put make our table. Let's put what your V is, your N is, and your delta S is. Okay, so we use our coordinate system. So this goes in the opposite direction. So you're in 1 and 2, got two openings. This is minus B1 in the J direction. You see, this is Y and Z. And then what else we have? This is uh, the unit vector is always going outwards. It's in this direction. It happens to be in the same Y direction. So this is J, and this is delta S1. Now in opening number 2, V goes in the same direction of Y. So this is V2 direction of Y. And J, and this is also the unit vector is going in this direction. Remember, it's normal to the surface. Here it was going also in this direction, but it's normal to the surface. Not, it has to go outwards, always outwards, not inwards. Okay, so that's why this is also going to be J, and the area is delta S1, S2, sorry. So what we can do is, let's con rho, okay, rho is the same. What we know in the problem is P, so we know what the P is. We do not know this P. So P2 is not known. So this is what we really know. You need to do this table before you get started. Okay, it's really helpful, especially get your vectors right, your directions right, plus minus sign is correct, and then you can move on. It's easy to move on. So now we go back to this problem, and now we replace all the values, and we see what happens. Okay, so the equation of the conservation of mass then tells me summation, oh, well, we already know what that is. So that would give me rho 1, V1 dot N1 delta S1 plus rho 2, V2 delta N2 delta S2, and that has to equal to 0. Okay, so let's replace each one of these guys. Go to the table. This is rho, it's all the same. So my density is the same. And what I have here is, this is minus V1J, and this is J. So this is minus V1J, and this is J, times delta S1. And this is rho. V2 would be V2J, and this is J. So this is V2J. Take the dot product J. Delta S2 is equal to 0. Okay, so this aspect right here, this gives you minus V1. This gives you V2. So your equation then becomes minus rho V1 delta S1 plus rho V2 delta S2 is equal to 0. And you can see that in this problem, I know this, I know V1, I know this, I know rho, I know S2, so I can find what I do not know. So I can solve for here and say V2 is going to equal to V1 delta S1 divided by delta S2. So this is the value of V2 that I need in this problem. Okay, so now we can go back to the equation and say, okay, so now we got V2. Okay, we got V2, so we are done. Let's go back to the Bernoulli equation so we can find the pressure. Okay, so second one is Bernoulli. Okay, and just remember, I'm using Bernoulli because I don't have heat transfer, it's incompressible flow, and the shear effects are not included in the problem. Okay, so the Bernoulli equation tells me P1 rho 1 plus V1 squared divided by 2 G Z1 is going to equal to P2 rho 2 plus V2 plus G Z2. Now note, it has to be in compressible flow to use Bernoulli, so that's why we just keep this to rho. We don't put rho 1 or rho 2. I just place it there just for the most general case. Okay, so let's look at the problem. Let's see what we have. What we got, we have this, we have this, we have this. Uh, we have your delta Z, and I will talk about that in a moment. Um, and this one I do not know. I know I just found this by the conservation of mass. This one I can also find its coordinates. So basically you will go in the problem and you will put a coordinate system and you can say this is my maybe Z1, okay, say it's equal to 0. And then you can come up here and say Z2, it will actually equal to H, okay? You can do that. You can just put this is the coordinate system where this is acting on. Okay, so you can say this is Z1. I'm going to start at 0. I'm going to start there. I'm going to start Z2 equal to H. Another way to do the problem is set this right in the middle, and this will be minus H over 2, and this will be plus H over 2. Regardless of whatever you do, it's fine. So I can basically, so this is known, okay? So I can basically solve for P2. So if I solve for P2, I solve for P2, and I can show that this is the equation that we get, V1 squared minus V2 squared divided by 2 plus rho G Z1 minus Z2, okay? And note, this is equal to 0. This is equal to H. So in my problem, I also note here in this problem, just so you can see that from here, another way I could also express this, I can come here and I can write this expression as follows. I can say this is rho V1 squared over 2, 1 minus V2 over V1 squared. But note that V2 over V1, if I go back to this equation, okay, V2 over V1 is equal to delta S1 divided by delta S2, right? So this whole thing can also be written as rho V1 squared 1 minus delta S1 divided by delta S2. All of this is squared. Okay, now this is important because many times this is what we use we multiply the velocity by a factor, okay? And there are other factors that we can consider. The area, may consider the losses in the area, but this is a very good way of doing this, okay? That's what we do. Okay, with that said and done, so then I can just say my P2 in my problem then is actually equal to P1 plus rho V1 squared divided by 2, 1 minus delta S1 divided by delta S2 squared minus rho GH. Okay, so all I have done now is I found P2. So now I come back here, I say, okay, I found my P2. Hey, now I have all these quantities, right? I have P2, I have V1, V2, V1, P1. I can just find my force. So now we use the last thing I'm going to use in the problem is my momentum equation. See, I'm not using everything in the same order that was given, because you just have to know what you have and what you need. So now we go to conservation. In this particular case, we can go to conservation of momentum. The conservation of momentum tells you the triple integral of r rho dv dt, the volume, is equal to the triple integral of r rho the body force minus over the enclosed area p and ds. Okay, so if you work with each one of these terms individually, you can show that, first of all, the very first term, because this is actually steady flow, this is the first term. Let me just write this down. This term right here is nothing else than the triple integral of r rho dv dt. And if you go back to your notes, we derived this for you. This is the triple integral of r partial of t rho v over volume plus the double integral over the enclosed area rho v dot n del ds. Okay, now this term right here will be 0 because this is steady flow. Okay, so this whole expression is equal to this. So my entire problem then basically becomes S V rho V dot N ds plus, going to bring all the closed integral on one side to keep it all positive, and ds is equal to the triple integral of r rho f d volume. Okay, so let's work with each one of the terms and let's see what happens. This is term number 1, number 2, and number 3. So I'm going to start with number 3 because it's a lot easier. The triple integral of rho f d volume. And in this particular problem, as you can see in the problem, z is going up, but my gravity is going down. Okay, so my z is going up, but my gravity is going down. So you expect this to be a minus sign. Rho g over volume is k. Now, if my z was going down, so if you had a case like this, okay, in this particular case, then it will be positive vk. Why? Because they all go in the same direction. This is not this. So this is if this was the case, okay? But this is the case that this is for our problem. So now, the next thing that you also know is we can go to item number 2. That's the double integral of p dot ds. It's nothing else than a summation of I equal to 1 to 2 because I have, again, 2 openings. And that would be pi ni delta si plus your force. Okay, now I put plus, assuming that my force goes in this direction. Okay, so as you can see in the problem, you can immediately see that your force is going to equal to Fyj, and my z component is actually equal to 0. Why? because you can see the flow is only acting in this direction. Okay. Um, However, no, wait a moment. Yeah, that's not true. That's not all that true because you have gravity force. Okay, if gravity wasn't acting, then this will be zero. Please correct that. If the gravity was not acting, then this will be zero. You will not have anything because the flow was coming only in this direction, but you do have a force coming in this direction. So you will have a force that will have a z component in this problem. Okay, so in the most general case here, this will be P1 N1 delta S1 plus P2 N2 delta S2 plus Fyj plus Fzk. Okay? Now we know all these quantities. We know what each one of these guys are. So, and we can replace those values in there. So my P1 is known, and go back to your table. This is J, so this is J times delta S1, that's known, and P2 is given by this expression right here. So I'm going to bring all this. Okay, so that is P2. This whole thing is P2 multiplied by my unit vector. Unit vector is J, so also J, and times delta S2. Okay, plus Fyj plus Fzk. So we have all this. Now all we have to do is, so we got this first one. All we have to do is find, we got 2, we got 3. Let's do number 1 now. Okay. So the expression number 1 is also the enclosed area of S. It is the velocity times the dot product unit vector over the enclosed volume. This is summation of I equal to 1 to 2. Again, we got 2 openings. Vi rho I v dot n times delta S1. So this expression gives you V1 rho 1 V1 dot N1 times delta S1 plus V2 rho 2 V2 dot N2 delta S2. Okay, so we will replace all the values in here. V2 is V1 is minus, so this is minus V1J. This is rho minus V1J dot N1 is J. So this gives you J times delta S1 plus V2 is V2J rho times V2J dot product J times delta S2. Okay, so we found this one. So next item is, let's go ahead and put it all together in here in this big expression. Okay, so we have 1 plus 2 is equal to 3. So in this particular expression, it's a little bit different from the previous example we did because I just kept 2 on the side. In the previous example, we had this on this side. I just decided for this problem to do it different. I kept it here. Okay, so it's all the same. So we're going to take expression number one, that's this expression, and let's simplify it. This gives you minus v1j times, okay, so this gives you is actually equal to the whole expression here. And I can take this expression on the next page. Before I add all this up, let me go ahead and do some simplification and just show you what the expression ends up being. The whole expression ends up being v1 squared plus delta s1 plus v2 squared delta s2. This is all j, right? Because this is j, this is j. I'm just simplifying the expression. Minus, minus, negative, negative becomes plus. So this is how I get this expression. I can further go ahead and just a little bit of mathematics here just to simplify my expressions a little bit. You don't have to do that. I often like to just remember I have what V2 was, so I can replace what V2 was there. V2 was equal to V1 delta S1 divided by delta S2. We found that. So I can replace everything and do a little bit of mathematics, and you can show that your end result actually looks something like this. Okay, this is a nice closed form solution to our problem. So now this is what 1 is actually equal to. So I'm going to go ahead and combine everything, put everything together now, and you can see that I will get the following. So I get the following. I get plus, so this expression, let me just copy it from here. So I just brought, this is expression number 1, and this is number 2, including this term right here. This is number 2. And now this is everything has to equal to expression number 3. Expression number 3. We just started with that expression. Where are you? This is equal to this expression. So all that stuff has to equal to rho g v k, and this is minus. Okay? So the best way to solve this problem is to say we can put all the terms in the z direction, all the terms in y direction. That's a lot easier. So your problem basically says that if I put all the terms in the y direction, so take all I components or j components, then this whole expression actually equals the following. I can take this whole thing, okay, and what I'm going to do is I'm going to set, you just take everything in the j direction, take everything in the j direction, and I just rewrote it, and that's equal to 0, and then I can solve for f. Okay, so solving for f, we basically say f is equal, so I'm going to write it here, so f y is equal to this whole expression that I have here, but it will be minus sign, right? Because I'm taking it on the other side. Okay, so this is minus, this is minus, and this is minus. And then I do the same thing with the z components. You take all the terms that have a k in this problem. So I come up here, I have k, I have k. So in that case, you see that Vz is equal to minus rho G V1 volume. Okay, and then with just one more thing, this is the total volume, but you can also know that your volume can also be expressed at the rate of the volume with time. Okay, and this is very common. We do this a lot, where this is the velocity one of delta S1. Okay, so this is how you find this volume. This is time. So we could express that this is actually equal to V1, rho G minus V1 delta S1 times time. Okay, you don't have to do this, but this is how we conveniently express this. Everything is in function of time. So as the time goes, you know how this is going to be changing. So this is the two problems. So this is the solution for F, Fy, and Fz. And the direction just tells you the direction in which your force is actually acting. Your entire structure is acting on it. Sorry. Okay. So this completes this particular example.